Space. For thousands of years, humanity has looked toward the night sky with the same question in mind. What is really out there? Maybe the universe is not just stars, planets, and empty space. Maybe hidden in the darkness are things so powerful, so terrifying, that they can bend time itself. Objects where light disappears, places where the laws of physics begin to break. And somewhere between science and mystery lies the truth humanity has been trying to uncover for centuries. Welcome to MystoReveal, the place where science meets the unknown, where mysteries become deeper, and where every question leads us closer to the secrets of the universe. Tonight, we are diving into one of the most terrifying creations in existence, black holes. Ancient civilizations saw gods in the stars. Sailors used constellations to cross oceans. Philosophers spent entire lifetimes wondering whether the universe had an end or whether it stretched forever into darkness. But among every mystery hidden in space, there is one object so terrifying, so powerful, and so strange that even light itself cannot escape from it. A black hole. The name alone sounds frightening. Something dark, something endless, a cosmic void waiting silently in the universe. And honestly, modern movies have made black holes even more mysterious than before. Especially one movie, Interstellar. When Christopher Nolan released Interstellar in 2014, millions of people around the world became obsessed with black holes again. The movie did not show black holes as simple dark circles floating in space. It showed them as giant cosmic monsters capable of bending time itself. And one scene in particular completely changed how audiences imagined the universe. The moment Cooper falls into the black hole Gargantua. At first, there is only darkness, endless darkness. Then small glowing particles begin appearing around the spacecraft, like grains floating in space. Sparks start flying across the screen. Fire surrounds the ship as it moves deeper and deeper into something no human has ever seen before. And suddenly, instead of dying instantly, Cooper enters a strange five-dimensional structure, where time itself becomes physical. He can see different moments from the past. He communicates with his daughter through gravity. Books move from shelves. Reality itself begins breaking apart. And after watching that scene, one question exploded across the internet. Could this actually happen? What truly exists inside a black hole? If a human being somehow fell into one, what would they see? Would they die immediately? Could time really slow down? Could black holes connect dimensions? Or are black holes simply giant cosmic traps from which nothing can ever return? The truth is far stranger than fiction, because black holes are not fantasy. They are real objects that exist in our universe right now. Scientists have detected them, photographed them, measured their effects on stars, and spent decades trying to understand how they work. But to understand black holes, we first need to understand gravity itself. Because black holes are not magical portals. They are gravity pushed to the absolute extreme. And the story of gravity changes forever with one man, Albert Einstein. More than 100 years ago, scientists believed time was universal. Time moved the same way for everyone everywhere. Gravity was treated as a simple pulling force between objects. The universe seemed predictable, stable, logical, but Einstein completely destroyed that understanding. In 1905, Einstein introduced one of the most important scientific ideas in human history, the special theory of relativity. At first, the theory sounded impossible. Einstein proposed that time itself could slow down depending on speed. Think about that carefully. Time is not fixed, it changes. Today, this idea feels familiar because movies constantly use time dilation concepts. But back then, it shocked the scientific world. Einstein discovered something strange while studying light. No matter how fast an observer moves, the speed of light always remains the same, around 300,000 kilometers per second, always. This creates a bizarre situation. Imagine two people, one standing on Earth, another traveling inside a spaceship moving near the speed of light. According to common sense, both should experience time equally. But Einstein discovered something unbelievable. The faster you move, the slower time moves for you compared to someone moving slower. This phenomenon is called time dilation. And yes, this is real science. Scientists have experimentally confirmed it many times. Atomic clocks placed inside airplanes show tiny differences compared to clocks on Earth. GPS satellites orbiting our planet must constantly account for relativistic time effects. Otherwise, your phone's navigation system would become inaccurate. That means relativity is not science fiction. Your smartphone literally depends on Einstein's theories. But why does this happen? Einstein realized that space and time are not separate things. They form one connected structure called space-time. Inside spacetime, speed changes how time behaves. Imagine traveling in a spaceship moving close to light speed. Inside the ship, everything feels normal. Your breathing feels normal. Your heartbeat feels normal. Your watch appears normal. But for people on Earth, your time slows down dramatically. A journey that feels like 5 years for you could become 50 years for people back home. Imagine leaving Earth while your parents are young and returning to find entire generations gone. This is why relativity feels both beautiful and terrifying. The universe itself allows time to stretch depending on motion. Scientists call this concept relativity because measurements of time are relative to the observer's motion. There is no universal clock controlling reality. Time behaves differently depending on speed and gravity. To understand how strange this is, imagine twins. One twin stays on Earth while the other travels through space near light speed. After many years, the traveler returns. According to relativity, the traveling twin would actually be younger than the twin who stayed on Earth, not because of magic, not because of freezing, but because time itself passed differently for both people. This idea is called the twin paradox, and experiments confirm that time really behaves this way. Suddenly, humanity realized something shocking. Time is flexible, and this becomes even more important near black holes. Because if speed alone can slow time, what happens near something with unimaginable gravity? Einstein answered that question in 1915, when he introduced the general theory of relativity. If special relativity explained how speed affects time, general relativity explained how gravity affects time. And this is where reality becomes truly mind-bending. Before Einstein, gravity was mainly understood using Isaac Newton's ideas. Newton described gravity as a force pulling objects toward each other. But Einstein saw gravity differently. He realized gravity is actually the bending of spacetime itself. Imagine spacetime as a giant stretched fabric covering the universe. Now place a heavy bowling ball onto that fabric. The surface bends downward. If smaller balls roll nearby, they naturally move toward the heavier object because the fabric itself is curved. That is similar to how planets orbit stars. The sun bends spacetime around itself, and Earth moves through that curved spacetime. Gravity is not invisible magic. Gravity is geometry. But Einstein discovered something even stranger. If spacetime bends, then time itself also changes near massive objects. Stronger gravity means slower time. This effect is called gravitational time dilation. Interstellar showed this concept perfectly. Remember the water planet near Gargantua? On that planet, 1 hour equaled 7 years back on Earth. At first, this sounds ridiculous, but it is based on real physics. The planet was orbiting extremely close to Gargantua, a supermassive black hole with unbelievably powerful gravity. That gravity distorted spacetime so severely that time slowed dramatically near the planet. For the astronauts, only hours passed. For people far away from the black hole, years passed. Think about how terrifying that would feel emotionally. You could spend a short amount of time near a black hole and return to discover everyone you love has grown old or died. Entire civilizations could change while only days pass for you. Gravity literally changes the flow of time. And scientists know gravitational time dilation is real because experiments confirm it constantly. Even clocks placed at different altitudes on Earth tick at slightly different rates due to gravitational differences. Tiny effects but measurable. Now imagine this effect becoming extreme near black holes. Einstein's theories also revealed another terrifying possibility. If enough mass bends spacetime strongly enough, then escape may become impossible. Not even light could escape. This idea eventually became the foundation of black holes. Ironically, Einstein himself was uncomfortable with the idea. Mathematically, his equations allowed black holes to exist, but emotionally he found the concept too strange. An object so dense that light itself becomes trapped forever sounded absurd even to him. And during Einstein's lifetime, the term black hole did not even exist yet. Scientists were still trying to understand the strange predictions hidden inside relativity equations. As physicists continued solving Einstein's equations, they discovered something shocking. The equations repeatedly predicted extremely dense collapsed objects, where spacetime becomes infinitely curved, objects from which nothing can escape, not even light. And suddenly the impossible started looking scientifically unavoidable. But before black holes fully enter the story, there is another incredible fact about gravity most people never realize. Gravity does not act instantly. This surprises many people because gravity feels immediate in everyday life. If you drop a phone, it falls instantly. But according to relativity, changes in gravity travel at the speed of light. Here is a mind-blowing example. Imagine the sun suddenly disappeared right now. Most people think Earth would instantly fly away into space because gravity vanished. But that is wrong. Because both sunlight and gravity travel at light speed. Sunlight takes about 8 minutes to reach Earth. Gravity also takes about 8 minutes to reach Earth. So if the sun vanished, humans would continue seeing sunlight normally for 8 minutes. Earth would continue orbiting normally for 8 minutes too. Only after those 8 minutes would darkness arrive and Earth's orbit begin changing. That is how deeply connected space-time truly is. Einstein's theories transformed physics forever. Over the following decades, scientists began studying what happens when stars die. And this is where black holes are truly born. Every star in the universe, including our sun, exists because of a balance between two powerful forces. Inside a star's core, nuclear fusion constantly occurs. Hydrogen atoms combine under extreme pressure and temperature to form helium, releasing enormous amounts of energy. This energy pushes outward. Meanwhile, gravity constantly pulls inward, trying to collapse the star. As long as these two forces remain balanced, the star stays stable. This balance is called equilibrium. But stars are not immortal. Eventually, stars begin running out of fuel. Imagine a giant fire slowly consuming wood. Over time, the fuel decreases and the fire weakens. Stars behave similarly. They spend millions or billions of years burning hydrogen in their cores. Our sun, for example, has a lifespan of around 10 billion years and is currently about halfway. Through its life, eventually hydrogen inside the sun's core will become depleted. The core contracts, temperatures rise, helium fusion begins. Larger stars continue fusing heavier and heavier elements over time, carbon, oxygen, neon, silicon, until eventually iron forms. And iron changes everything. Unlike lighter elements, iron fusion does not release energy. It absorbs energy instead. That means the star can no longer support itself against gravity. The balance breaks, gravity wins. The star collapses inward catastrophically. For massive stars, this collapse creates one of the most violent events in the universe, a supernova explosion. For a brief moment, a supernova can outshine entire galaxies. Massive shockwaves blast through space while the core compresses under unbelievable gravity. And something beautiful happens during these explosions. Many heavy elements necessary for life, including gold and silver, are forged inside supernovas. The atoms inside your body were created billions of years ago inside exploding stars. Humanity is literally made from stardust. After the explosion, the remaining core determines what forms next. Smaller remnants become white dwarfs. These are extremely dense stellar cores, roughly the size of Earth. A single teaspoon of white dwarf material would weigh several tons. If the remaining core is heavier, gravity crushes matter even further, forcing electrons and protons together into neutrons. This creates a neutron star. Neutron stars are unbelievably dense. Imagine compressing the mass of an entire star into an object only around 20 kilometers wide. A teaspoon of neutron star material would weigh billions of tons. Some neutron stars spin incredibly fast and emit beams of radiation, like cosmic lighthouses. Scientists call these pulsars. But if the remaining core is even more massive, gravity becomes unstoppable. Nothing can stop the collapse. The star compresses smaller and smaller until gravity becomes so extreme that escape velocity exceeds the speed of light itself. And because nothing travels faster than light, nothing can escape. A black hole is born. One scientist played an incredibly important role in understanding this process. Subrahmanyan Chandrasekhar, an Indian-American astrophysicist whose discoveries revolutionized stellar physics. Chandrasekhar discovered there is a maximum stable mass for white dwarfs, around 1.4 times the mass of our Sun. Today this is known as the Chandrasekhar limit. If a stellar remnant exceeds this limit, white dwarf stability becomes impossible. Further collapse occurs, potentially creating neutron stars or black holes. This discovery became one of the foundations of modern astrophysics. And thankfully, our Sun is below this limit. That means the Sun will never become a black hole. Instead, billions of years from now, it will eventually become a white dwarf after passing through its red giant phase. But much larger stars face far darker destinies. As scientists continued studying collapsed stars during the 20th century, evidence for black holes started growing stronger. Strange X-ray sources appeared in space. Stars were seen orbiting invisible massive objects. Something unseen but incredibly heavy seemed to exist. Throughout the universe, then, physicists realized black holes come in different types. The most common type is called a stellar black hole. These form when massive stars collapse after supernova explosion. Their masses usually range between 3 and 100 times the mass of our Sun. Scientists estimate our Milky Way galaxy alone may contain millions or even billions of stellar black holes. hidden across space. Then there are primordial black holes, theoretical objects possibly formed during the early moments after the Big Bang due to density fluctuations. These black holes remain hypothetical because scientists have not confirmed them observationally yet. Some theories suggest they could even help explain dark matter. Next come supermassive black holes, the true giants of the cosmos. These monsters exist at the centers of galaxies and contain millions or billions of solar masses. Our own galaxy, the Milky Way, contains a supermassive black hole called Sagittarius A star located around 26,000 light-years from Earth. And yes, Gargantua from Interstellar was based on a supermassive black hole because their enormous size allows some unusual relativistic effects to occur more smoothly. Scientists even photographed supermassive black holes recently using the Event Horizon Telescope. The famous orange glowing ring image released in 2019 became one of the most historic astronomical achievements ever. Humanity had finally captured an image of a black hole's shadow. But despite the name, black holes are not simply dark invisible balls floating in space. They possess incredibly complex structures. One of the most important features surrounding black holes is the accretion disk. This is the glowing ring of gas, dust, and debris orbiting around the black hole at enormous speeds. Gravity pulls matter inward while angular momentum forces it into a rotating disk. Inside the accretion disk, particles move near light speed. Friction and compression heat the material to millions of degrees. The matter transforms into plasma and emits enormous radiation, especially X-rays. Interestingly, the glowing orange color, commonly shown in movies and images, is mostly for visualization purposes. In reality, much of the radiation would be invisible to human eyes. But scientists use colors to help people understand the structures. Visually, another strange effect appears around black holes called gravitational lensing. Einstein predicted gravity could bend light itself, and black holes demonstrate this dramatically. Light traveling around a black hole follows curved paths. Because space-time itself is warped, this creates bizarre visual distortions. Parts of the accretion disk hidden behind the black hole can actually appear above and below it due to light bending around the object. This is why Interstellar's black hole looked so strange and beautiful. Scientists working on the movie carefully modeled realistic gravitational lensing effects based on Einstein's equations, and suddenly black holes become even more terrifying. Because near them, reality itself stops behaving normally. As scientists continued studying black holes, they realized something even more terrifying. Black holes are not all the same. Some are relatively small, created by collapsing stars, while others are gigantic cosmic monsters sitting silently at the centers of galaxies. And understanding these different types of black holes completely changes how we look at the universe itself. The most common type is called a stellar black hole. These form when massive stars die in supernova explosions. Remember the balance we talked about earlier. Outward pressure from nuclear fusion fighting inward gravity. Once that balance collapses inside a massive star, gravity crushes the remaining core smaller and smaller until space-time itself bends beyond escape. Stellar black holes usually contain between 3 and 100 times the mass of our Sun, but all that mass is compressed into an unbelievably tiny region. Imagine taking something larger than our entire solar system and compressing it down to the size of a city. That is the level of density involved. Scientists estimate that our Milky Way galaxy alone may contain millions or even billions of stellar black holes, hidden throughout space. Most remain invisible because black holes themselves emit no light. We usually detect them indirectly. Sometimes a black hole steals material from a nearby companion star. That material forms an accretion disk around the black hole and heats up to extreme temperatures, releasing massive X-rays. Scientists observe those X-rays and realize something invisible but incredibly massive must be present there. Then there are primordial black holes, one of the strangest theoretical ideas in cosmology. These black holes may not come from dying stars at all. Some scientists believe they could have formed during the first moments after the Big Bang itself. Right after the universe was born, space-time was incredibly chaotic, hot, and dense. Tiny fluctuations in density may have become extreme enough to collapse directly into miniature black holes. Some theories suggest these primordial black holes could be as tiny as atoms while containing the mass of mountains. Imagine holding something smaller than a grain of sand that weighs more than Everest. It sounds impossible, but relativity allows such objects mathematically. The interesting part is that scientists still have not confirmed primordial black holes observationally. They remain hypothetical. But some researchers think they could even explain dark matter, the mysterious invisible substance making up most of the universe's mass. If primordial black holes exist, they could completely transform our understanding of cosmology. But even these strange objects are nothing compared to the true giants of the cosmos, supermassive black holes. These monsters sit at the centers of galaxies and contain millions or even billions of times the mass of our Sun, our own galaxy. The Milky Way contains one called Sagittarius A star, pronounced A star. It lies around 26,000 light-years away from Earth and contains roughly 4 million solar masses. Think about that carefully. 4 million suns compressed into one region. And our galaxy is not unique. Scientists now believe almost every major galaxy contains a supermassive black hole at its center. Some are so enormous that their diameters rival the size of our entire solar system. For decades, supermassive black holes remained theoretical because humans had never directly observed one. But in 2019, history changed forever. The Event Horizon Telescope project released the first direct image of a black hole in galaxy, M87. The image showed a glowing orange ring surrounding a dark shadow. Humanity had finally photographed the edge of a black hole. That image became one of the greatest scientific achievements in modern history. Over 100 years after Einstein predicted black holes mathematically, humans finally captured evidence of one visually. And interestingly, the orange glowing ring looked very similar to the black hole shown in Interstellar. That was not coincidence. Christopher Nolan's team worked with Nobel Prize-winning physicist Kip Thorne to make Gargantua scientifically accurate. In fact, the movie's visual effects were so realistic that some scientists later used the rendering techniques for actual astrophysics research. Now there is another possible category of black holes. Scientists continue searching for intermediate black holes. These would exist between stellar black holes and supermassive black holes, with masses ranging from hundreds to hundreds of thousands of suns. Evidence for them exists, but confirmation remains difficult. Astronomers have detected unusual X-ray sources suggesting intermediate black holes may exist, but research continues actively. So suddenly the universe feels crowded with invisible monsters of different sizes. Tiny hypothetical primordial black holes, stellar black holes formed from dead stars, intermediate black holes hiding between categories, and gigantic supermassive black holes controlling the hearts of galaxies. But despite the terrifying name, black holes are not simply dark balls sucking everything around them like cosmic vacuum cleaners. In reality, black holes possess incredibly complex structures, and understanding those structures is where things become truly mind-bending. The first major structure surrounding many black holes is called the accretion disk. This is the glowing ring most people associate with black holes visually. Gas, dust, stars, and debris orbit around the black hole at enormous speeds, forming a rotating disk. But why does the disk form instead of everything simply falling straight inside? The answer is angular momentum. Objects in space are almost always moving sideways while gravity pulls inward. This combination creates orbital motion, the same reason Earth orbits the Sun instead of crashing directly into it. Near black holes, this orbital motion becomes extreme. Matter spirals inward at incredible speeds, sometimes approaching the speed of light itself. Friction between particles heats the material to millions of degrees. The gas transforms into plasma and emits huge amounts of radiation, especially X-rays. This means accretion disks are among the brightest objects in the universe. Ironically, the brightest regions near a black hole come from material desperately trying not to fall inside it. And here is something fascinating most people do not realize. The orange-yellow color commonly shown in black hole images is mostly for visualization. In reality, much of the radiation emitted would be invisible to human eyes, especially X-rays. Scientists and filmmakers use visible colors so humans can better understand the structure visually. Interstellar's depiction of Gargantua was especially famous because it showed another bizarre phenomenon accurately. Gravitational lensing. Einstein predicted that gravity bends light itself. Black holes demonstrate this effect dramatically because their gravity distorts spacetime so severely that light follows curved paths around them. This creates strange visual illusions. Normally, if you look at a glowing disk from the side, the back portion should remain hidden behind the object. But around black holes, light from the back bends over and around the black hole toward the observer. This makes parts of the accretion disk appear above and below the black hole simultaneously. That is why Gargantua looked so unusual in Interstellar. It was not artistic exaggeration. It was relativity in action. Imagine how terrifying that would look in reality. space itself twisting light into impossible shapes, the universe appearing visually broken. Scientists call some of these distortions Einstein rings or photon rings, and they represent one of the clearest demonstrations that space-time itself can bend. Now things become even stranger. Around black holes exists another region called the photon sphere. This is an area where gravity becomes strong enough that light itself can orbit the black hole. Think about how insane that sounds. Photons, particles of light traveling at the fastest speed possible in the universe, can become trapped in circular orbits around a black hole. Inside the photon sphere, reality behaves in ways completely outside normal human experience. Theoretically, if a person somehow survived there and looked sideways, they might see the back of their own head because light emitted behind them could curve completely around the black hole and return to their eyes. The photon sphere represents one of the strangest places predicted by physics. But the honest scientific answer remains simple. We do not know. And that uncertainty makes black holes even more fascinating. Interstellar explored some of these unknown ideas creatively. The movie showed Cooper surviving inside Gargantua and entering a 5-dimensional tesseract, where time became navigable like space. Scientifically, this part becomes highly speculative. String theory and some advanced physics models discuss extra dimensions, but humans currently have no evidence that people could experience time physically in this way. Still, the movie deserves enormous respect because much of its black hole science was surprisingly accurate. The accretion disk, time dilation, gravitational lensing, all based on real equations. Only the deeper interior concepts moved into science fiction territory. And honestly, that is what makes black holes so incredible. The boundary between science and imagination becomes blurred because reality itself already feels unbelievable. Even now, scientists continue studying black holes intensely because they may hold answers to humanity's biggest questions. How gravity works at quantum scales, whether information can truly disappear, how galaxies form, perhaps even how space-time itself behaves at the deepest levels of reality. And the deeper we study black holes, the more one thing becomes clear. The universe is far stranger than human beings ever imagined. Now imagine the impossible finally happens. You are floating in space, staring directly at a black hole. Not through a telescope, not through a movie screen, but with your own eyes. Behind you lies the rest of the universe. Ahead of you exists something humanity barely understands. A region where gravity becomes so extreme that reality itself begins breaking apart. And the terrifying part is this. Once you get too close, there is no turning back. For decades, scientists and filmmakers have asked the same question. What would actually happen if a human being fell into a black hole? Would death be instant? Would your body explode? Could you survive for even a few seconds? Or could black holes hide something even stranger beyond the event horizon? The truth depends on the type of black hole. If you approached a smaller stellar black hole, the gravitational difference between your head and feet would become enormous long before reaching the event horizon. Your feet would feel dramatically stronger gravity than your head. This difference is called tidal force. And those tidal forces would begin stretching your body vertically while compressing it horizontally. Scientists jokingly call this process spaghettification. But despite the funny name, the reality would be horrifying. Your bones, muscles, organs, even atoms themselves would stretch into an ultra-thin stream of matter. Death would come before you ever crossed the event horizon. However, things become stranger near supermassive black holes. Because supermassive black holes are so enormous, their event horizons are much larger. This means tidal forces near the edge become weaker. Theoretically, a person crossing the event horizon of a supermassive black hole might not die immediately. In fact, they may not even notice the exact moment they crossed it. And that idea alone feels terrifying. Imagine floating across an invisible boundary knowing escape has become physically impossible forever. Now let us break this journey into phases. The first phase begins during approach. As you move closer to the black hole, gravity becomes stronger and stronger. Time dilation also increases dramatically. To people watching from Earth, your movements would appear slower over time. Your voice signals would become stretched and distorted. Light coming from you would slowly shift toward red wavelengths, eventually fading almost completely. But from your own perspective, everything would still feel normal. This creates one of the strangest effects in relativity. Two observers experiencing completely different realities simultaneously. To you, time feels ordinary. To distant observers, you appear frozen near the black hole forever. Meanwhile, the universe around you begins visually distorting. Gravitational lensing bends light from distant stars into warped rings and strange curves across space. The accretion disk surrounding the black hole glows brighter and brighter. Radiation levels increase dramatically. The sky itself begins looking unnatural. And then comes the second phase, crossing the event horizon. This is the true point of no return. Once inside, every possible future path through space-time leads deeper inward. Escaping would require moving faster than light, which according to current physics is impossible. And yet, for a supermassive black hole, you might still feel physically fine at first. That is what makes black holes psychologically terrifying. The event horizon is not a solid wall. There may be no dramatic sound, no giant explosion, no cosmic gate. You simply cross a boundary where the universe no longer allows escape. Outside observers would never actually see you disappear completely, because time dilation near the event horizon becomes extreme. To them, you appear to slow endlessly near the edge, but from your perspective, you continue inward normally. Then comes the third phase, the unknown. Because beyond the event horizon, modern physics begins collapsing. Scientists have several theories about what might happen inside black holes, but no confirmed answers. The first and most accepted possibility remains: spaghettification leading toward destruction at the singularity. Eventually, tidal forces become so extreme that matter itself tears apart at atomic scales. But other theories suggest reality may behave differently inside black holes. One idea involves the holographic principle. This theory suggests information falling into a black hole may not truly disappear. Instead, information could somehow become encoded across the event horizon itself like data stored on a cosmic surface. Another controversial idea proposes firewalls, ultra-high energy barriers, near event horizons that could instantly destroy anything crossing them. However, scientists still debate whether firewalls actually exist. Then comes perhaps the most fascinating theory of all: wormholes. Some solutions to Einstein's equations mathematically allow black holes to connect distant regions of space-time, potentially even other universes. These hypothetical tunnels are called Einstein-Rosen bridges. Science fiction loves this idea. Portals connecting galaxies, gateways through time, shortcuts across the universe. But there is a major problem. Most calculations suggest wormholes would collapse instantly before anything could pass through them. So while mathematically interesting, stable traversable wormholes remain speculative. Interstellar explored these concepts creatively through Gargantua and the Tesseract sequence. In the movie, Cooper survives inside the black hole and enters a yin five-dimensional structure where time becomes a physical dimension he can move through. Scientifically, this becomes highly speculative territory. String theory and certain advanced physics models do discuss extra dimensions beyond normal spacetime. Some versions predict 10 or 11 dimensions total. But currently, humanity has zero experimental evidence proving humans could experience time physically the way Cooper does in the movie. Still, Interstellar deserves enormous credit because much of its science was surprisingly accurate. Christopher Nolan worked closely with physicist Kip Thorne to make Gargantua realistic. The accretion disk, time dilation, gravitational lensing, all based on genuine physics equations. Only the deeper interior concepts crossed fully into science fiction. And honestly, that balance between science and imagination is exactly why black holes fascinate humanity so deeply. Because they exist at the boundary between what we know and what we still cannot understand. Now, there is another huge misconception people have about black holes. Many believe black holes are giant cosmic vacuum cleaners sucking everything in the universe toward them. That is completely wrong. Black holes only become dangerous if you get extremely close. Imagine replacing our sun with a black hole of identical mass. Surprisingly, Earth's orbit would remain almost exactly the same. We would continue orbiting normally because gravity depends on mass and distance, not whether the object is a normal star or black hole. The only difference is that sunlight would disappear. Earth would freeze, but the orbit itself would continue. This proves black holes do not randomly consume entire galaxies. Stars orbit supermassive black holes safely all the time. Our own Milky Way galaxy revolves around Sagittarius A star without danger because we are extremely far away. In reality, black holes obey gravity laws just like other objects. And surprisingly, black holes may actually help galaxies evolve. Scientists believe supermassive black holes influence star formation, galactic structure, and cosmic evolution itself. So instead of viewing black holes only as destructive monsters, scientists also study them as engines shaping the universe. And perhaps the most incredible thing about black holes is how humanity discovered them at all. Think about it carefully. More than a century ago, Einstein developed strange mathematical equations describing spacetime. At the time, even he doubted some predictions physically existed. But decades later, scientists began finding evidence proving those bizarre predictions were real. First came theoretical calculations, then came indirect observations, then came gravitational wave detections from black hole collisions. Then humanity photographed one directly. Science slowly transformed black holes from impossible mathematical monsters into observable cosmic reality. And yet, despite everything we have learned, black holes still hide enormous mysteries. What truly happens at singularities? Can information actually disappear? Does quantum mechanics change the interior structure completely? Could black holes connect spacetime in ways we do not yet understand? The honest answer is simple. We still do not know. And maybe that uncertainty is exactly why black holes continue capturing human imagination. Because they remind us how small our knowledge still is compared to the universe itself. Every generation believes it understands reality. Then the universe reveals something stranger. Once humanity thought Earth was the center of existence. Then we learned Earth orbits the sun. Then we discovered billions of galaxies. And now we study objects capable of bending time, trapping light, and warping spacetime itself. Black holes are proof that reality is far more mysterious than human intuition. And somewhere out there, hidden in the darkness between stars, countless black holes continue silently shaping the cosmos. Maybe one day humanity will fully understand them. Or maybe black holes will always remain cosmic reminders that some mysteries are bigger than us. But one thing is certain. The deeper we explore the universe, the stranger reality becomes. And honestly, that is what makes science beautiful. Because every answer leads to even bigger questions. So the next time you look up at the night sky, remember this. Somewhere in that darkness may exist an invisible object powerful enough to trap light itself. A place where time slows, space bends, and physics approaches its limits. A black hole. And humanity is only beginning to understand it. If you enjoyed this journey into the universe, then make sure to subscribe to MystoReveal for more deep documentaries about space, mysteries, science, and the unknown. Every week we explore questions that challenge reality itself and take you deeper into the hidden side of existence. Like the video, share your thoughts in the comments, and tell us one thing. What do you think exists inside a black hole? Because maybe, somewhere beyond the event horizon, the universe is hiding answers humanity was never meant to find. Until next time, keep questioning reality.